In this video, we will show how to use Python to work with lognormal distribution. So first, we take a look at lognormal distribution. So if a continuous random variable x, if we take the log form of x, y has a normal distribution with mean mu and standard deviation sigma, then we can say x has a lognormal distribution. And the mean and variance of the lognormal distributions have this form. So this mu is the log form of x's mu. Then we plus sigma square divided by 2 and take e of power of this part. Then this mu is the lognormal's mean. And the lognormal's sigma square equals also the e's power part. And in the power part, these two parameters are log of lognormal's parameter. Then times e's sigma square minus 1. And these two figures represent the density function of lognormal variables with different mu and sigma. So in Python, if you want to use lognormal distribution, we have to import scipy.stats module called lognorm. Then we can use 4 functions: lognorm.pdf, .cdf, ppf, and rvs. And therefore, the density, cumulative probabilities, quantiles, and random number generation, respectively. Just keep in mind that in the function a and b, a means the mean of the lognormal variable, and b is the sigma. So if we take a look at density function, so in the Python's function, the mean of the location parameter is for this one, not this one. Not this one, is this mu, is the lognormal variable's mu. And the sigma is for this mu, sigma. Because lognormal density function has some little different form, but this is the quite normal form. So next we will show examples in Python. We import scipy's lognorm and numpy and matplotlib. We will create a quantile array between 0.01 to 10 with the gap 0.5. Because the lognormal variables available value must be larger than 0. So we set a equals, for example, a equals 0. Here, a 0, b is 1. So which means this location parameter refers to lognormal variable. So this is what we finally want to be interested in, not the log of the lognormal variable here. So this is the mean for the lognormal variable. We set 0 and sigma set 1. This is the sigma in the density function. Or sigma is the sigma of the log of the lognormal variable. So be careful of this parameter. And we set a is 0, b is 1. So next we use the function called lognorm.pdf to generate the density values of this array of variables from 0 to 10 with this location and shape. Sigma also called the shape parameter. We plot this density. So you can see the density from 0 to about 0.62 increase very fast. This is change very fast between 0 and about 0.25. Then decrease fast, then slowly close to 0. And the area under this curve close to 1. So if we set a equals 5, b equals 2 here, you see the location is 5, so location is 5, so the mean value is here. So the curve moves, but shape does not change so much. Shape does not change so much for this one. But here, because location is 5, so the value lower than this value equals 0, the density. The next function we will show is CDF, called cumulative probability function. So we set A 0, B equals 1 by default and calculate the cumulative probability associated with this quantile array between 0 and 10. Then we plot the relationship. So cumulative probability is not decrease, and the beginning is increased very fast because the density is quite high, then slower, then almost close to 1. So the highest probability is 1, right? And next function called ppf is to calculate the quantiles from given cumulative probabilities, and this operation is actually the inverse operation of the cumulative probability. So from given cumulative probability, we have to calculate the random variable values. So we set A and B same as before. Next, we create an array called probs to represent probability between 0.01 to 1 with the gap of 0.1. Because probability can be no larger than 1, so we set from 0.01 to 1. Then we can use the function lognorm.ppf to calculate the quantile variables associated with the probabilities array and with the parameter A and B of this lognormal distribution. You can plot the relationship between the probabilities, cumulative probabilities, and the quantile variables. So for example, for the 0.6 represent the cumulative probability 0.6, the value is almost 1.25. So we can say 1.3 about, so we can say almost 60% of the variables in this lognormal distribution less than 1.3, right? The last function we have to introduce is random number generator. So we want to generate lognormal random numbers, 32 such random numbers. So we create n equals 32, A and B. This time we set A is 5, B is 2. You can use lognorm's RVS function. Set a location A, size B, SB, shape as B, size is n. The size is the number we want to generate, how many random numbers. You can print these generated numbers. You can see very close to 5 because we set the location equals 5, mean value equals 5. With the log of these log normal variables, standard deviation equals 2. So the variation, so the number as large as, for example, 34 has been generated, and most of them around 5, between 5 to 10. So thanks for watching.